I will introduce myself a little bit here. I have been a long time DuckDB contributor, so since like early 2020, something like that. Thanks to Hannes, because he didn't want to implement recursive CTEs, essentially. And at this point, I started my work on user-defined functions, which I will be talking today. And I knew that, well, eventually I want to implement the stuff in DuckDB, and I would need recursive CTE, so I ended up to implementing them myself. I'm also around when there's something wrong with like query decorrelation, also in like the optimizer at some places. But in my day-to-day life, I'm technically from academia, with a strong focus on like query optimization, execution engine design, and user-defined functions, or more specifically, how to get rid of them, which is quite ironic to present this project today. I'm also really interested in like compilers and programming languages, which will become important in a second. So, I want to talk a little bit about the state of DuckDB UDFs. So the system does support macros, which is like a simple textual replacement you can use for simple expressions. I'm sure they are great and there are many users of it. However, what you can't do is like have an if statement, then do some stuff if a condition is true, or do some other stuff if the condition is false. You can't put like a create table into this stuff and return something. I'm aware that most of you probably end up using Python or R to define your UDFs, which is great, but I think it kind of breaks like the single file zero dependency database promise DuckDB provides. And that's essentially where I want to step in. That's the idea behind DuckPL, to fix all this stuff and essentially give you an interface for pgSQL inside of DuckDB. That's the whole idea. And what I want to provide is essentially the possibility for users to have UDFs, so user-defined functions, like the one on the left, right inside your database system. So what we have here is just a little example that just computes like the number of steps the collects conjecture needs to reach like 0 or something like that. The interesting part here is I can have like a while loop, I can have like my if statements, I can have variables in my code, and I, of course, can return some values and call this function. If you talk to people from Germany, from my university, they will just tell you, okay, you don't need UDFs, just use SQL, like the one on the right, which may be easy to do in this case because the UDF is relatively simple. But in general, it's not so easy, especially if your UDFs become complex. Still, we don't need to have any external dependencies if we can execute these functions right inside the system. And that's the first thing I want to do. I want to just show you how it works. So I have my DuckDB running here. It's just an in-memory database at this point. And I can just copy-paste this collects function, which we just saw on the slides, paste it in here. And now we have the function registered inside the database system, and we can just call it. So it works, it computes a value, simple as that. So I have like my loops, my ifs, whatever I want to do right inside my system. Of course, I can also make this a little bit more interesting by using just more values like this. And it still works, essentially. So it provides the user with more means of using the database system without relying on external dependencies, essentially, external runtimes. Okay, to make this demo work, we do have like a few components I do want to dive a little bit into in the next few minutes. So starting on the left, we have like this PL SQL input. In this case, it's the Postgres dialect because DuckDB as well relies on the Postgres parser. So we just copied that. I will talk a little bit about the parser, but not too much. Next, we will have a transformation. That's exactly the same thing that's happening in the system. We have persistent storage because these UDFs will be stored inside your database file. And of course, we have an executor that can execute these functions. And in terms of APIs we use, we are, of course, a parser extension and we are an operator extension to be able to essentially hook into the binding and planning phase of these functions. So, parsing the missing pieces. The Postgres parser usually supports these language constructs. However, Mark decided somewhere in 2018 that we don't need it, that we don't want it, and he just threw it all out of the system. Means that we have to parse two things, and we need two parsers to achieve that. We have to be able to parse the create function statement, essentially, and we have to be able to parse the pgSQL body. If you know SQL, these two $ imply that the body is indeed just a string, so we can parse this as a literal. Okay, this looks a little bit like this. The whole parsing is split into two phases. First, we parse the create function statement. Then we parse the PL pgSQL body. And we just rely on the libpgquery parser infrastructure for that, at least for the time being. The system, DuckDB, is switching to a peg parser, and we will do the same thing here. But in the second part, we need to get rid, essentially, of these Postgres data structures we have inherited by that by using a transformer, meaning that we transform this Postgres abstract syntax tree into our own representation. And I do want to talk about that now a little bit. Because if you ever looked at Postgres, please don't, you will be aware that there are like 5 different AST nodes that can be used for nodes, because you have like 3 or 4 different for loops that you can use. If you loop over an integer, it's a different loop than if you loop over a query result, for example. We don't do that because the internal representation we use for these programs is actually syntax agnostic, because we want to be able to swap out the front end, essentially, because at this point we want to have Postgres compatibility, but in the future, in line with like this friendly SQL approach DuckDB has, we want to have another language in front. And that's kind of the idea here. So what we do is we have like this really small language that's powerful enough to express all your computation, and the user don't have to interact with this. But it means that if you have like this while loop, for example, in the middle, we don't want to have a while loop. We just have like this forever loop. It loops forever. And we introduce like a break. So that's essentially the equivalent of a goto-based program at this instance. So this simplifies a lot of stuff in the long run, because we will be able to just easily introduce new front ends like PL Python maybe, or a DuckDB specific language. We are planning that, and it will come in the future. Good. In terms of storage, we have like this problem that we want to have persistent UDFs, and it's not that easy to extend the catalog because there are not that many hooks at the moment that would allow us to do what we are doing here. So we just stole the idea from Duck Lake, how they approach macros, and we just store our UDF definitions in a table, which is really simple to do. It's really small. You have all the benefits of encryption, for example, and we can just load up, essentially, the defined definitions at startup time of the extension, which simplifies just this whole storage infrastructure. What you could do is just store like the pgSQL block as a code that the user provided. Problem is you would have to pass the functions at every invocation, or at least at startup time every time. We don't do that. Instead, we additionally store like the function body in an AST form as a blob. So we can just serialize into the DuckDB format. Okay, in terms of execution, there's one point I do want to talk a little bit about. At this point in time, we do implement like a simple tree walk interpreter. However, we employ a trick. Because if you have a tree walk interpreter, you just use like the C++ core stack, essentially, to store your state. That's a problem in the context of DuckDB, because you can't pause and resume execution. And especially in context of a table-valued function, which I will show later, this will just fill up your memory without using the infrastructure that the DuckDB executor provides. So what we do is we use an explicit stack, which we can just manage on the heap instead of the stack, which allows us to essentially just push new stack frames depending on what happens. And I do have like a simple example here that's just the execution of a loop. So on the left, we have like the loop. So essentially the pointer points to your current code position, if you want to put it like that. If we put the loop on the stack, and then we just continue inside the loop. So we have to check the if condition, that's now in the middle. We push a new frame on the stack that essentially encodes, okay, now on the stack top we have like the PL if. And then we can just check, okay, is this condition valid or not? And depending on it, we either go to the break or return next. In this case, we don't break, so we continue to the return next. Return next in PL pgSQL just means, okay, I do have a table-valued function, and I do add another value to the result. And that's the top of the stack. And at that point, we can just check if we have space left on the data chunk we are currently filling, which allows us to either pause execution at this point or just append new rows, which allows us to stream results without buffering. And this looks a little bit like this. We have another function here that's the infinite function, which returns a set of big ints, so just a table of numbers, essentially. That's a really nonsensical function, by the way. But what we have is a loop that never terminates, just counts up numbers, and returns values. So this will never return. This will just run infinitely. And if you try this function on Postgres, that's exactly what happens. So you start execution, and it will never finish. It will never return anything. It cannot be interrupted with a limit, for example. That's not possible. With the execution principle in DuckPL, we do return, because we can just copy like the behavior of physical operators in DuckDB. We fill the chunk until it's full. If it's full, we return, control back to DuckDB, and just say, okay, yes, we have more output here. And either the system decides, okay, yes, we need more output, or it's finished. Those are the choices, essentially. which allows us essentially to have early termination in this case. And I want to show that behavior quickly. So that's the same function we have seen on the slides. So just quickly register it. And what you can do now is to have this query, which essentially says, okay, I want to read from this infinite function. It's a table-valued function, so I can use it in the from part of the query. And I want to read like 10 times 2048 rows, so in DuckDB lingo, so to speak, 10 data chunks. And if you execute it, it just works, instead of just looping forever, which is exactly what would happen without the limit clause. It would just run and run and run and run and probably kill my MacBook at some point. So let's not do it. Another thing you can now do is you can just combine these two functions I have created. So we have collards and we have infinite, and we can just use them in combination essentially. Or we cannot, because that's a typo. We didn't pray to the demo gods. That's the problem here. And now it just works. So if you get your variable names right, it works. So essentially, we can define infinite functions, streams, what some people call them, and just use them. And it works. Okay. One last point, because we are a developer meeting, I want to dive a little bit into is efficiency and execution. And a big part in these PL interpretation systems inside of database systems is expression evaluation. And what I have highlighted here in these black boxes are SQL expressions, essentially, because while we do add like these while loops, etc., we do not add expressions. It's all just SQL in here, which means if we do it the slow way, we would just wrap all of this, like the 0, x greater than 1, inside of a select statement and just execute that. And you can imagine if this loop runs for like 1,000 iterations, that's a lot of queries you are executing here, which is really, really, really slow. The way we do it is a little bit different. We want to use the expression executor directly, which is not supported by the system, but we still do it because we can. What we do is, in a nutshell, that's vastly simplified here, we prepare like this query, like select x greater than 1. We just extract like this x greater than 1 expression from the statement we get. And instead of running the whole like query executor on a whole data chunk, etc., we can just use the expression executor directly and execute it against the data chunk. And the result is not bad. We are about 30 times faster for this function here if we use this fast path of execution. So this is really important at this point. Not the end of the road, but I will talk about that now. So now, so to speak, the state of DuckPL, because it's not even open sourced yet. It's not out there. You can't use it yet. But there's quite a bit of support we have already. So users can use scalar functions. They can use table functions, variables and assignments, all data types, even user-defined data types. You can use composite types like table types. So line item, for example, if you use like the TPCH database. In terms of control flow, we are feature complete. So you can use if all types of loops, break, continue, return, and return next. So we are Turing complete at this point. We even have support for cursors with simple operations. So we can fetch into variables, but we don't have advanced cursor operations like jumping, like scrolling, like moving yet. Also, we do have like attempts of debugging. Essentially, printf debugging is possible at this point using race. That's just like the printf equivalent of PL pgSQL. What is not supported, not now or never, is dynamic SQL, but I'm happy to discuss that. My point of view is that DuckDB already has like the query function that allows you to do it. So we don't have to support it on our end as long as this function exists. With query, you can just input a string and get a result. So this just, should just work. In terms of advanced cursor features, that's not planned. Currently, we will see how this project will be received by the community and how the demand will be. And because DuckDB doesn't support triggers, at least at the moment, we won't be supporting triggers. Pull requests welcome. In terms of what's planned, we want to have the ability to not only register as scalar or tabular functions, but also as aggregate functions and window functions. That's something that Postgres, for example, supports. Exception handling is a big topic, so your try-catch semantics, that's on the table. Transactions, that's a huge topic, because essentially you currently get like nested connections, which is a problem we have to solve. And also a UDF optimizer, which I will talk about in a second. But maybe to address like the elephant in the room, compilation to pure SQL. Because for a lot of these UDFs, you don't need the DuckPL executor at all. Because you can just express it using pure SQL functions, using with recursive, for example. And that way, we would be able to, on the one hand, massively improve performance by just leveraging DuckDB's execution engine. And that's like the future where we are heading. And in terms of infrastructure, architecture of this whole system, we will end up somewhere here. So the gray boxes are essentially exactly the same as before. But what I want to do is essentially have like a UDF optimizer. We don't optimize anything at the moment. We just execute a UDF as the user provides it. There's a lot of optimization potential there left on the table. Also, what I want to work towards is like this execution dispatcher. Because if we take a look at the system right now, we just have like this interpretation path. So all functions will be interpreted using the DuckPL executor, which can become slow. That's fairly good understood. But on the other hand, that's what I have done like the last 6 years, is like establish compilation frameworks to get rid of these UDFs, compile them to SQL, and that's like the other path. So if we can, we want to compile to SQL to get like massive speed-ups out of this. And in the far future, we want to combine it. We want to have like this partial compilation where we can just interleave interpretation with the SQL compiled code to have like the best of both worlds, essentially. That's the idea. Currently, we can just interpret, but we are working on the compiler. Okay, a little bit more future work, maybe the vision of this whole thing. Postgres essentially just gives you the option to define functions and call them inside of your queries. I think it would be a really nice addition to have like a REPL-like experience right in the CLI of DuckDB. That's not implemented currently, sadly. But what I want to have is like, for example, a let statement I can just issue to define a variable y in this case, have like a loop, do some stuff, print some stuff right inside the CLI, so that you can just use the DuckDB CLI instead of the Python CLI, for example. That's the idea. We will see how that works out. We will move to the pack parser infrastructure to simplify a whole lot of stuff. Of course, use all the research we have done on these UDF compilations and essentially work towards productizing this whole idea. Okay, in conclusion, we will start by establishing compatibility first. So we want to have Postgres compatibility because there are lots of code bases out there which could just switch from Postgres to DuckDB in like a minute or so because we have like this compatibility layer. We don't have a learning curve because this stuff is known and LLMs can generate it, honestly. Then we want to have smart execution. So instead of just having like the compatibility, we have the speed we are after. And in the end, we want to have like the hybrid execution and the CLI features. All right, obviously I'm biased with all this UDF stuff, but that's all I had to say. Happy to answer your questions.
Thank you, Denis. In the interest of time, let's do a rapid round of questions.
Thank you so much. Maybe a small question. I didn't really get if the execution engine that you have built is also applying all the vectorization and all the...
Not yet.
So it's a single thread at some
yes.
point.
Currently, it is row-by-row execution. We want to change it, obviously, but it's the first version. We are not even in the alpha.
Okay.
Thank you.
Yeah, thank you for a great presentation. I was hearing you saying that you compile or more or less parse while loops into a generic loop kind of structure and then break out of it.
Yes.
So you can't reverse compile it from your whatever tree to the source code.
We don't have to because we just store the user input.
Exactly. Yeah. Yes. And I was wondering about that. Do you do that? Because that would be really handy, right?
Yes, we do that just in case.
Yeah, of course. Cheers. Thank you.
Hi. Hi. A great presentation, very interesting topic. Have you looked into, or just out of interest, because you mentioned that performance and interpretation is kind of a bottleneck.
Yes.
Maybe it's crazy, but like, would it not be possible to kind of use something like V8 and or at least some JIT compiling thing that already exists and use that to actually translate or transpile the procedure code to something like that?
I mean, yes, I have done extensive research on this. Your bottleneck is not the interpretation. Your bottleneck is like this impedance mismatch between imperative and declarative execution of SQL.
Okay.
That's your problem. And you can't solve that with JIT, for example.
Okay.
Cool, thanks a lot. If you have any more questions, you will have to catch Denis during the snacks and bites. So thanks for, well, talking about this and hopefully shipping this soon, Denis.
Thank you.